In this session, we will derive the equation for distribution factor. The distribution factor for an alternator, or it is also called as a breadth factor, is defined. It is a ratio of EMF generated in distributed winding to the EMF generated in the concentrated winding. It is usually denoted by the KD and its value is always less than unity. Even in the case of the coil span factor is Kc, which is also less than the 1. Here, what do you mean by concentrated winding? If the set of conductors which is meant for one particular phase under one pole, if they are placed in a single slot, then it is called as a concentrated winding. That is, the conductors pertaining to one particular phase under each phase is placed under one slot is called as the concentrated winding. Similarly, instead of having only one slot for one particular phase conductors, instead of placing in one slot, it is distributed in so many number of slots under each pole, then it is become a distributed winding. That is, in the concentrated windings, all the conductors or coil sides are bunched together and placed under under each pole under one particular slot. That is what we are calling is concentrated winding. If those conductors of a particular phase under each pole is distributed in the different slots, then it is become a distributed winding. The same thing is defined here, the concentrated winding in which all the conductors of a given phase per pole are concentrated in a single slot. Whereas in the case of the distributed winding, when the slots are distributed around the armature uniformly, the winding that is inserted is called as the distributed winding. That is, the winding which is distributed for one particular phase under each phase under each pole is called as the distributed winding. That we can elaborate with the help of one small numerical example here. I got a 3-phase 4-pole 36 slot machine. I got 3-phase 4-pole 36 slot machine. Here I have got a 4-pole, then I have got a 36 slots are uniformly distributed in the periphery of the armature. Then what I am doing here is these 36 slots I am distributing for 4 poles. Therefore, what I am calling is the number of slots per pole. The number of slots per pole is 36 divided by 4. Therefore, we can observe here the change in the color of the conductors. This 9 slots are for R, for first N pole. This next 9 slots is meant for second pole, that is S pole. Next 9 slots is meant for this N pole, this 9 slots. Then the remaining 9 slots is for the final pole, that is S pole. Here we have distributed the slots for 4 poles, that is the number of slots per pole. At the same time, the number of slots per pole is nothing but the pole pitch, that is equal to 180 degree also. Now, once again these slots under each pole can be distributed for 3 different phases because we are studying the 3-phase alternator. Therefore, this 9 slots under each pole should be once again distributed for 3 different phases R, Y and the B. Just you can observe here. I have got the number of slots per pole per phase is 36 divided by 4 into 3, that is 3. That is 3 for R phase. Previously I have got this 9 slots for this N pole. Out of this 9 pole, first 3 are for R, the next 3 are for B and next 3 are 5 phase. Similarly here also the conductors are distributed for R, B and Y. Under the next pole also once again these are distributed for R, B and Y. Here also that is R, B, Y. Means the number of the conductors first distributed for each pole Under each pole, it is redistributed for each phases, that is 3 for each phases. I am distributing here for 36 slots 4 pole machine. Now, I told you from the center of the N pole to center of the S pole, that is what we are calling as pole pitch, that is equal to the N. N is nothing but the number of slots per pole, that is equal to 9 here. Now, the angle which is subtended for pole pitch is 180 degree, which is a constant, that is 180 degree electrical, that is equal to the pole pitch. Now what I am interested in the angle between the adjacent slots, If we are taking this particular example here, there are 9 slots are distributed for 180 degree. Therefore, the angle between the two slots is 180 divided by 9, that is equal to 20 degree. Means then how to get the angle between the slots? It is merely 180 divided by the number of slots per pole, or 180 divided by N formula that you have to make use of. Therefore, the same thing is defined here. The angle between the adjacent slot is represented by the angle beta. That is, it is represented by the angle beta. Therefore, here the angular displacement between the two adjacent slot is defined as B. B is equal to 180 divided by the number of slots per pole, that you have to look into. That is, this is the formula you are using. That is, the number of slots per pole is nothing but it is N. That is, the number of slots per pole is nothing but the N. Okay. Now we'll go for, this is what we are calling is, you are distributing the number of slots throughout the periphery of the armature, and under each slot, under each pole, once again the conductors are distributed for, slots are distributed for each phase R by B. Then if you are placing the conductors in these slots, then the resulting current is, resulting winding is called as distributed winding. It is called as distributed winding. Whereas I have got only one slot under one pole, that is, there are 3 slots. In all 3 slots under each pole, that is, each slot is meant for each phase. This is for R phase, B phase and Y phase. Then whatever the conductors which is pertaining to R phase, are all conductors are placed in a single slot here. Similarly, all the B conductors of a particular phase under each pole is placed under this slot. Similarly for the Y phase. Then all the conductors are concentrated and placed in a single slot. Then this winding is called as concentrated winding. For example, I will take, there are 3 conductors are placed for R phase, 3 conductors for V, 3 conductors for Y. In the previous case, it is 3 conductors are distributed, whereas here 3 conductors are placed in a single slot. The 3 conductors are the single slot. If you are placing the 3 conductors in a single slot, there the induced voltage in each coil side or a conductor is ECS. Therefore, the total voltage, how much you are getting? 3 times ECS, because the phase displacement between the conductors, that is the induced voltage under each slot, is remains same, because all the induced voltages are in phase. Therefore, what I am getting here is, that is, ECS is the induced voltage in the one conductor, ECS is the induced voltage in the second conductor, ECS is the induced voltage in the third conductor. All these 3 conductors are placed in a single slot. Therefore, they are all algebraic sum, 3 voltage we are getting. Therefore, 3 times ECS we are getting. This is for concentrated winding. It's a concentrated winding. Then, to define KD, what you need is, it is a ratio of the induced voltage in the distributed winding to the concentrated winding, or it is the ratio of the vector sum to algebraic sum. The algebraic sum you are calculated, that is 3 times ECS. What is the 3 here? What is the 3 here? What is the 3 here? It is a 3 is nothing but It is a number of slots per pole per phase. That is nothing but your M. M is the number of slots per pole per phase. Therefore, what I am getting is the total voltage general equation in the concentrated winding. It is M times ECS. It is M times ECS, the total induced voltage in the concentrated winding in an alternator. Okay. Now we will go for, instead of the concentrated winding, I am distributing the conductors. Therefore, what we are getting here, there is one conductor here, the induced voltage is ECS here, there is a same voltage is inducing the second conductor, and in the third is also the induced voltage remains the same. However, the phase displacement between the first voltage and second voltage is beta, and the phase displacement between the second and third is once again it is the beta. It is not algebraic sum in the case of distributed winding. That I am explaining here. The same thing is explaining here. See here once again. Okay. See here. There is a conductor here has got a ECS. Here also ECS. Here also ECS. But the phase displacement between each induced voltage is the 30 degree. Therefore, how we are getting the voltage? That is the ECS here. That is the induced voltage in the one of the conductor. Then the second conductor is also same voltage, because the induced voltage is depending upon the speed of the rotor, magnitude of the magnetic flux, and the nature of the armature. All the armature conductors are used are uniform, or the same material, same length, everything is same. Therefore, the magnitude of induced voltage remains same, but however there is a phase displacement of the beta degree between the first and second, second and third, and so on. Therefore, it is beta here, that is a 20 degree in this case, because we are finding out the beta is 20. Therefore, here another is 20 degree here, and total is, this is the resultant voltage for R phase under each pole for each phase. What you are getting means, this is how you have to get the total induced voltage in the distributed winding. If it is a concentrated winding, straight away you are getting 3 times ECS. But in the case of distribution winding, you are not getting the sum of all the 3 voltages. It is a vector sum of the voltages which is spread in the different slot under each pole. Now we have to generalize this equation. Therefore, I am defining the beta. The beta is already defined. It is an angle between adjacent slots, and the value of the beta, which is calculated as beta is equal to 180 divided by number of slots. That is nothing but 180 divided by n. Then we also defined m. M is nothing but these are the number of slots per pole per phase. Number of slots per pole per phase. Then how we are finding out? It is 180 divided by P into 3 in the case of 3-phase alternator. Then there is one more terminology we are defining here. It is M beta. This M beta is called as phase spread. What do you mean by phase spread? That is, you can see here from this is meant for R phase. This phase is meant for phase. Then how many slots we are distributing? M number of slots are distributing for each phase. Therefore, it is M beta. And the another set of slots is distributing for the next phase. This is also phase spread, that is also M beta. And the remaining is also for the M beta. Is it not? This is called as phase spread. It is called as phase spread. Means the angle which is subtended for a set of slots under each pole for each phase is called as phase spread. Okay. Here the same thing I am written here, that is m beta. M beta is phase spread angle, that is for it is angle of slots which is assigned for each phase under each pole. Then how many the slots are there? That is m slots for each phase under each pole. Therefore, m vectors you are getting a such AB, you are getting how many vectors? M number of vectors you are getting. Their phase displacement between each other is the beta. I am showing here AB is 1, the second one is the ECS. There are so many things are added here. It is M number of this such vectors are added and finally you are getting the resultant. Therefore, the final, once again there is another, the last vector I have shown here, that is ECS. This is m number of ECS. 1, 2, 3. For the previous example I have got m is equal to 3. Therefore 1, 2, 3. Or if m is equal to 6, then such 6 vectors are added with a phase displacement of b with each other. Then from starting to end what we are getting is the total resultant. Here I am getting the total resultant voltage. It is because of a distributed winding. It is because of a distributed winding. Then from the center O, just I am joining all these vectors, that is A, B each, m number of vectors, and I am assigning AO value as R for calculating the distribution factor. Just I am assigning AO is equal to R. Then we know that the angle between the adjacent slot is the beta. Here is also beta, and such how many vectors we are adding? It is a m number of vectors are adding, therefore total angle subtended here is it is m beta. Then I am making the two construction line. One is I am dropping from AB, that is one of the induced voltage, coil voltage, and another one is I am dropping a perpendicular from the center of the resultant. One is from the resultant vector, the another perpendicular I am dropping from the one of the induced voltage in a coil. Now what I am doing here is I am interested in the voltage induced in the distributed winding, that is I want to calculate AE. I want to calculate AE. Therefore, how I am proceeding? Just I am taking these two construction line, then I am finding AB. The AB is nothing but just I am taking one as the intermediate point, that is I told you this as point N you can take. If we are taking from OAN, then we know that from this particular triangle, that is AB is equal to 2 times AN. AB is equal to 2 times AN. Then how to find out AN? It is applying the sine function for ANO triangle. Sine function for ANO triangle. In that case, sine beta is equal to AN divided by AO. Therefore, AN is equal to R times sine beta by 2. That is R times sine beta by 2. That is AN, what we are getting is R times sine beta by 2. But what I am interested is AB. It is nothing but 2 times AN. Therefore, what I am writing here is 2R sine m beta by 2. Similarly, it is an arithmetic sum. Such m number of vectors I am adding. Therefore, it is m times 2R sine m beta by 2. Then, from the another triangle from AEO, or in the intermediate point you can take here, that is as here as a m. From triangle AMO, once again you can calculate the value of the value ER, that is AE is equal to 2 times AM. From AM, from the triangle it is m beta by 2, that is 2R sine m beta by 2. That is you have to find out AM. Once again you apply sine function sine m beta by 2 is equal to AM divided by R. Therefore, AE is nothing but 2 times AM. Therefore, what we are getting? to our